Hello everybody. I just thought I'd share some information with you guys. I've been playing with simulations of ways of replacing the pots, log or logarithmic pots, or multi-turn pots, whatever you want to use there in your variable voltage power supplies. As some of you may already know, your voltage regulators are able to accept a DC voltage onto the adjust pins, or many of them can, and this will in turn allow you to actually vary your voltage output on the regulator based on the voltage that you're putting onto the reference pin or the adjust pin. So what I've been looking at is ways of taking a digital signal from our ATmega328 or our Arduino and actually converting that to a digital analog signal. Now there's many ways to do it. Some of them is using pulse width modulations. I've decided to go the route of a digital to analog converter. In this case I'm using a serial controlled MCP4725. If you have a look, it's over here. It's a little 6-pin device, very small, tiny little fella, and it's controlled with these two lines over here. This specific one, unlike the ones that you get on the breakout boards, is controlled with a slightly different address, but I'm not going to get into all the addressing and stuff like that just yet. I'm just trying to show you what actually happens. So what you do is you connect your supply to VDD, your ground to VSS, your V out is obviously your analog voltage output. Your two control lines are your SCL and SDA lines. If you have a look here on your Arduino, you're using the SDA, SCL and connecting them together. On the Uno it happens to be A4 and A5. A0 is an address pin, don't worry about that, you can leave that open. I'll show you now on the Arduino software. Your address which you'd set, which is default for the standalone chip, is 0x60 as a hexadecimal. So DAC begin, you need to get this Adafruit MCP4725 library, but like I say, that's not what this tutorial is about. This just initializes the DAC. This gives the DAC its addressing so that we know exactly, well, the Arduino knows exactly what to call it. This is pretty much a command just to convert to a decimal number so we can count from 0 to 495. Don't stress too much about it, I'm not going into detail. What I've done here in this code is I'm going to just reduce this over here so we can see it at, well no, let's leave it like that for now. What I've done is I've done several things. I've set the counter to 495 and then I've written that to the DAC. So what that would do is the DAC would actually run at 5 volts, 495 being the max, 0 being the minimum. So 495, we'll get 5 volts output, 5000 millisecond delay. Then I set the counter to 2048 and write that value to the DAC again, which should give us 2.5 volts. Then I've set a delay again, and then I've done a counter. So it's basically a 4 counter. So what will happen is from 0 to 495, counter plus, which will basically increment by 1. And then DAC set voltage counter, delay 100, so you can actually see it happening. And then basically delay 5000 once it's done through the whole procedure and back to 5 volts. But now bearing in mind it's already at 5 volts, so it'll slip straight into that 5 volts there, no problem. So what I'm going to do here is just compile the sketch. So we can get our hex file, run it in the simulator. Takes a bit of time sometimes. Right, there's our sketch is compiled. So now we're going to go into our emulation software here, DAC control, and we can run the simulation. So first step, like I said to you, would be your 5 volts. 5 seconds, you should switch now to 2.5 volts. There we go, our 2.5 volts. Then the next step, it'll go into that count. Now I just want to show you the accuracy of this in the count. Once it starts counting, it's going to go from 0 volts to 5 volts. but this is going to be the increments that you can actually set by. As you can see, you can set 0,01 volts, 0,02 volts. So you have a very fine control over your voltage at this point from 0 to 5 volts. Now obviously you can't really use this as a 0 to 5 volts power supply because this isn't capable of very high currents. But you can use it to control various regulators, which we will get into at a later stage. Let me just recompile this code with less of a delay. Let's go with maybe a 20 millisecond delay. Compile the sketch. Again, it might take a few minutes. Seconds, actually, not minutes. I don't know why it takes so long when I have multiple applications open. Okay, we're done compiling, so let's just, it should actually pick it up, but I just want to reopen it per se. Now let's execute it. Now that up count from 0 to 5 volts should happen a lot quicker. Okay, we're going to start at our 5 volts, then it'll drop to the 2.5 volts, and then it'll start the up count a little bit quicker than it did the last time. So we can see the actual range of 0 to 495. There we go. We start counting up. This will count all the way up to 5 volts and then back down. Well, if I set it to back down to 0, but it'll count to 5 volts and it'll stay there currently with the code that's been written. I'll get into how this helps us control regulators in the next episode. I hope you guys all enjoyed it, and until next time. Hi everybody. I decided today, well, yesterday, to actually take the basic LM317 power supply, which is above here, and take it a step further. I haven't completed this yet, obviously, but I'd just like to show you the work in progress so far. What we have here above is the standard AC voltage, transformer, relay switching. I haven't applied any switching to this point here yet to get our 30 volts, so we're currently running at about a 15 volt rail. Bridge rectifier, capacitor. So here is basically where our AC gets converted to DC. Just a bit of filtering. Our adjustable LM317 voltage regulator. This resistor over here usually forms part of the voltage divider. You'd normally have a 470 and maybe a 10k variable here, and then your set point would be sitting in the middle over here to get the control voltage. But what we're actually removing that, and what we're doing is we're giving the control of the adjustment pin to the digital to analog converter and the microcontroller, but we'll get into that now. So this is now disconnected. Well, it is connected to something. It's connected to this point over here by a virtual wire. So the voltage regulator still requires some form of load. So what I've done is I've put a 470 ohm resistor across the output so that there is still a load present. That's just to get it down to its 1.25 minimum volts. Then we have some more filtering, some capacitance over here and stuff like that. So, but pretty much what you have over here is your controlled regulator. What I've done is I've built up a basic control circuit here based on the Arduino Uno for simplicity of everybody else. At the end of the day, I'll just build it off the standard AVR and burn the code directly to the AVR, no bootloaders or anything. But for simplicity, everybody knows the Arduino. So what we have here, just to explain, this is our Arduino. Our LCD, data pins are connected. Your LCD, RSE are all connected here to the Arduino. I've put 5 buttons on at the moment, but at present the code is only making use of these 2 buttons here, as in voltage up, voltage down. I'm still fine-tuning the timing, etc., for the speed and various other aspects of this, and possibly the steps. But for now, it is literally counting from 0 to 4095, which is the range of the digital to analog converter. So the digital analog converter is an I2C device, so it's basically controlled with 2 pins off the Arduino. This A0 pin number 6 is actually an address pin. We leave that open so it's at the default address. The output of this is obviously now connected to the adjust pin on the LM317. If you have a further dig into the design over here, what we have left to do is to implement code here for possibly a mode adjust or your voltage range. This could possibly become the voltage range to switch this in. This would be your fast adjust, and this would be your slow adjust or coarse and fine on the digital side, or possibly presets and fine adjust. So you could jump like between your regularly used voltages 1.5, 3.3, 5 volts, 9 volts, 12 volts, and then use this to adjust, or possibly use this to adjust per volt and this to adjust the millivolts. So yeah, there's a lot of opportunity here. I'll get into that a bit of a later stage. The next step that I need to do is what happens here with this specific setup is we are limited by the set voltage. This DAC will do 0 to 5 volts. So at 0 volts on the set pin, theoretically we should have 1.25 volts on the output. Let's just power up. This is a little boot screen I'm making for the power supply. And I need to get the timing and get that to reset early, obviously, in the code. But basically there we go, we have our 1.25 volts. Oh, before I go any further, this PSU out is connected here to A0, also on the Arduino, and we've got that measuring voltage 0 to 5 volts. So let's just bear in mind the Arduino can only go 0 to 5 volts on the read pin. But anyway, back to this over here. We have our 1.25 volts with our 0 volts on the set pin, which is coming in here. Excuse me. Now, if this won't be able to read it, obviously, because the Arduino can't read to 6.25 volts. But if we output the full 5 volts at this point over here, what do you think we're going to get you? Okay, I'll tell you what we're going to do. I'm going to disconnect the set point at the moment, and I'm going to inject the signal directly in. We're going to go with a DC signal. Okay, so 0 volts, 1.25 volts out. Okay, now bear in mind I've disconnected this section from this point here, although it is still going to read the PS out, don't worry about it. The beauty of this sort of thing. Then you come in over here, our 5 volts. So just to tell you, what do you think you're going to get? Remember, 1.25 at 0. So theoretically, at 5 volts of input on the adjust pin, we should be getting 6.25 on the out. And there it is, 6.25 volts. Okay, so you basically see that's the limitation of driving the DAC direct to the adjust pin. Let me just reconnect the DAC so we can see exactly what's going on there. Okay. We have it back to normal. You power on, and once it settles we'll have our 1.25 volts, and we can vary it by varying the DAC voltage. Okay, now like I said, it is a bit slow. We'll push and hold, and as this voltage increases, so you'll see the actual voltage on the output and on the LCD display increasing. Absolute fine control of voltage. If you displayed more numbers over here, you would be able to see how much fine control you actually have over those voltages. There's a few other things to look out for. Precision voltages are very handy for working on things like voltage controlled oscillators, where the slightest change in voltage adjusts the frequency, etc. But obviously you want a little bit more fast control, which we will get into later. For now, this is doing exactly what I've anticipated. But now what we need to do is think about, we're limited to the output of 6.25 volts. So now I'm going to be implementing an operational amplifier circuit. I'm not going to build it step by step here. It will appear in a few seconds, which will go between the set pin or the voltage out on the DAC. It'll increase the voltage out from 0 to 5 to maybe 0 to 30 or 0 to 25. Let's make it a 25 volt supply. From 0 to 25, and we'll input that onto the set pin over here, which should give us now a range of, it depends on the op amp. It could be anything from about 2 volts up to 26.25 volts. So let me put that together and I'll be back. How's it, everybody? Okay, well, I've ditched the op amp idea and I've decided to rather go for something a little bit more in line with what is current for me. Everything is the same as what you saw previously. The only difference is I've changed the code. Let's just bring this across here. If you have a look at the Arduino code here now, what I've done is I've added in a section for like a preset 5 volts, preset 3 volts or 3.3 volts, just to try it out, and then I've punched in their value to get them to exactly where I want them, and then obviously you can still fine tune with your standard up downs. So I'm thinking presets along with variable might be a good idea. At the moment I'm keeping this power supply under 6.25. Reason being is most of my prototyping, electronics, Arduino stuff, that sort of stuff is all below 5 volts and below. So really there's no need for me to get another power supply that can go higher than that. I already have 2 or 3 laboratory grade DC power supplies that are capable of up to 30 volts, some up to 20 volts. So really it would be a waste for me to get another one. What I wanted is something a little bit more precision, specifically for use with my digital stuff. And I think I may have found exactly what I'm looking for in this case over here. Obviously this code needs to be expanded quite a lot more because I can do a lot more with the presets. For instance, I could have a whole bunch of presets and then you just use the buttons to scroll through them. But yes, we'll see how it goes. For now what I've done is let's just power on the simulation over here. And what I'm going to do next is actually add a relay in over here to cut this power while the system boots up, and then once the system's booted, the Arduino will give the instruction to switch the relay on. But for now, yes, here we go. We've got our 1.25 volts base. I've got the presets put in, so we'll pop the 3.3 volt button. There we've got a measured out 3.3012 volts, 3.3 volts, and I've got a 5 volt preset. Bang, there it is, 5.0010, sorry, 5.0095 volts. So yeah, that's pretty accurate for me. As you can see, you can swap and change between these two presets as much as you like. And the beauty of this is I can, let's say I want 4.9 volts specifically. I can now bring this down. Like I say, I still need to play with the timings to exactly where I want it. Bearing in mind also the computer lags a little bit compared to the actual device with the timings, so it's very difficult to show you the actual timings on the computer, but you're getting the gist of it. It does work very well for all intents and purposes. So let me get back. Hey, how's it, everybody? I'm back. Okay, besides a protection diode, which you should put across an inductive load of any sort, and possible transistor switching, what I've done is I've just wired it directly for example purposes to the Arduino pin. This, you could actually use a non-inductive digital type relay, or non-moving part relay, solid state relay, whatever you want to call it. But what I've done just for example purposes is I've connected this to ground and to pin 7, and I've added some code here in pin 7 where basically on pin 7 I've told it that on pin is an output, and then I'm doing just a digital write on pin high right at the end of the code. So once the library starts up and everything's up and running, we power up the supply, everything's working. Our power is actually dead because there's no output at the moment, but as soon as the power supply is ready, it'll flick this relay and give us our, there we go, on. You see, we're in on position now, and we've got our output voltage displaying. So now as you run through your presets, everything is as it was. You can do your manual adjustments of your voltages here, and this relay pretty much just keeps the power on as long as this microcontroller is telling it it's on, which, as I showed you in the code, straight digital right, on pin high. I basically did that to take care of the fact that the DAC, the digital analog converter, runs at 2.5 volts before it's received any information. So it's pretty much outputting 3.75 volts before we even actually have anything ready to function. This could be a problem if you've got a 3.3 volt project hooked up or something like that, and you forget about this and you power the power supply on and it runs at that 3.75 volts for the 3-second boot. That could create a problem. It might not, but for me it was a bit of an issue, hence the fact why I've come in with a relay. So let's just show you guys again the functioning of this. You power on, you have your boot screen, you'll actually have 0 volts. This is just trailing a little bit or showing you the previous value. And as soon as the microcontroller is ready and everything is powered to where it should be, the last program step is to switch this relay on, which then allows the voltage, current, whatever, to flow out from the power supply. And then of course you can come in with your presets and do whatever you like. So that is just the basic steps of sorting out the issue with the voltage being high. What I'm also going to do to the software is to add code to the switch over here where I can manually switch this low and high. So the power supply will switch on and then switch high, possibly leave it as low, but we'll see how it goes. And then you can push this button to switch this relay off or switch the output off, and then push it again to switch it back on. Once I've done that, I'll show you guys, but I'm not going to rush into that because it's a simple thing. It's not something that's going to take a lot of my resources and time. So I'll get to that sort of later when I actually am in the mood for it. But for now, that's where we are. The precision power supply is 100% operational. Hey everyone. Just a bit of a follow-up in the final episode for this week on the power supply and the Arduino control and measurement of the power supply. What I've done now is I've pretty much added a shunt resistor, a series resistor with output to ground. So this would be your ground point, obviously, and then this would be your positive point. So what happens here now is analog 1 connects to this point, power supply unit current, PSU current, connects to A1 and allows you to measure the voltage across this resistor, which is obviously dependent on the current. Now I'm not going to dig into all the code, but what basically happens now is instead of just having our voltage measurement, everything happens as per the original. Power supply gets ready, bang, 1.25 volts, this switches on over here, and then you have your amp scale. I'm still going to be adding a watts or power scale to this power supply, which will allow people to see the current wattage being consumed, or various other information we'll add as we go. But for now, this pretty much finishes off this power supply. We have our presets. I need to make some slight adjustments to those presets just to make sure they're 100%, and everything is fully functional. So guys, thank you very much for watching this introduction to control of power supplies, or digital control of power supplies. I am going to complete this power supply and do a full video about it and how it works, but that will be following in the next 2 to 3 weeks. In the meantime, next week I'm going to start some basic tutorials on the Arduino. Things like taking the Arduino off the Arduino, well, taking the Atmel processor off the Arduino boards and actually building your own Arduinos. So if you guys want to learn a little bit about Arduino, or if you're just starting out, watch this space next week, and it